right, so today we're going to actually start off with vectors and scalar quantities. All right, and then we see how far we can go and cover for today. All right, so we know that vectors and scalar quantities, so vector quantities are quantities that has size, magnitude, and direction, and scalar only has size or magnitude, right? So we see here that we have different types of quantities that are grouped as scalar and some that are grouped as vector quantities, all right? So that's from CSEC level. All right, so let's look at our new things now. All right, so let's just group these according to being vectors or scalar. So I'm going to need your help. So you're going to tell me which one is which. All right, so let's go with mass. So is mass a scalar or a vector?
Scalar.
A scalar. All right, and weight?
Vector.
Vector. All right, speed?
Scalar.
Scalar. And velocity?
Vector.
Vector. Acceleration?
It's due to gravity, so I'd say vector.
Acceleration is vector, yes. Force?
Vector.
Yes, vector. Pressure?
Scalar.
Scalar. All right, temperature?
Scalar.
Scalar. Energy?
Scalar.
Yes, scalar. Moment?
Moment of a force. Vector.
Vector, yes. All right, time?
Scalar.
Scalar. Distance?
Distance is scalar and displacement is vector.
All right. All right, so that was just revision from our CSEC level, all right? So let's look at resolving vectors, all right? So with resolving vectors, these are things that you should be aware of from math or CXC physics, all right? So adding vectors, we add A and B to give us the resultant being R, all right? So that's what's happening here. So let's look at resolving our vectors. All right. So in CSEC level, you looked at only vectors in one vector acting in just one plane. All right. But for CAPE, we're going to look at when one vector actually acts in both planes or X and or Y plane. All right. So in these cases, we're going to have a vector that has both a X component and a Y component. All right, so let's look at how we would resolve that vector if it has both components being X and Y. So if we look at that vector below, F, right? So we notice that it's not going down vertically or across horizontally, right? It's slant. And because it's slant, then that means it has both an X and a Y component. So the X component would be the FH there, so the horizontal, and then the Y component would be the FV, the vertical, right? So this is where we use the idea from math, because we have an angle between it and the horizontal. So this angle is opposite to our vertical, right? And it's adjacent to the horizontal. So if we need to find what the horizontal component FH is, right? And if it's adjacent and it's the hypotenuse, then that means that is cos, right? So it would be cos of the angle. So it would be your force F times cos theta. And that would be for your horizontal component, or you would use X component. And therefore for the Y component, it would be, instead of cos here, we would have been opposite, it would be sine theta, all right? So that knowledge will be used frequently when we're going to look at some examples. All right, so let's move forward. All right, so we get those two there. All right, so let's look at this example. So it says a glider is launched by an aircraft with a cable. At one particular moment, the tension in the cable is 620 newtons, and the cable makes an angle of 25 degrees with the horizontal. Calculate the force pulling the slider horizontally and the vertical force exerted by the cable on the nose of the glider. All right, so the first thing is to make a sketch of the question if there is no diagram present. So in this case, we have the plane, we have the glider, right? So this is the tension force being 25 degrees to your horizontal, right there. All right, so in that case, we have the tension force here being 25 degrees right there, right? So in that case, we notice that there is a X component right there, and there is also a Y component right there, right? So this Y component on this side here is the same as if we continue this line here and an arrow going down there. It's the same Y component there. So this Y over this left side is the same as this Y on this side, right? So with that knowledge, then we can actually go ahead and complete our question. All right, so let's go in completing this question. So all right, so you're going to tell me now what would we write. So the first thing is to find FH. So in finding FH, what would we start off with? So FH, the horizontal component, would be equal to, yes, anyone?
F cos theta.
So we have the F cos theta, right? And now we can substitute F would be the tension, which is 620, right? Times cos theta, the angle there is 25. All right, so when you put that in your calculator, you should get
500.
what's that? 561.72. So you get 561 point.
So it's 562.
All right, so if you round it off, yeah. So you get 562 newtons. Right? So that's your horizontal, and then the next part says your vertical component, which is your y. So that would be your F, and in case of cost, this time we put sine. Right? So it is 620 sine 25, and that's its
262.
262 newtons. All right, so this one here is easy, right? Because it's just one vector. So it's easy to find its components being x and y. All right, so now we're going to use this knowledge to go further and see how well we can understand when it's more than one vectors. All right, so like in this case. So in this case here, we have a mass of weight 120 Newton is hung from two strings shown in the diagram below. Determine by calculating the tension in RA and the tension in RB. All right, so with this question, we have to actually redraw these questions with just the forces and your angles present. All right, so the first thing to note in this question is that the system here is in equilibrium. Right? So that's important to know that the system here in equilibrium. So that means that this downward force being provided by the 120 force or object is the same as an upward force here of the same value. All right, because once it's in equilibrium, there is no movement, so that means the downward force equals to your upward force. Right? So that means if we know that tension is an opposing force, so that means these forces tension will be going opposite to the weight or the load, right? So those are the angles there. And then if we continue these here, right? So we now see that we have two triangles. So one on this side, let's call it triangle A, and then we have one on this side, which is triangle B. Right? So we have this side of the triangle, which is the 120, right? We have the angle, so we can find these tensions here, tension 1 and tension 2. All right, so let's go. How would we find the tension? Let's look for first one, RA, so this side here. So let's call it tension 1. So tension 1 would be equal to
Sine 40.
what do we have for this side?
We have cos.
Right? So we have this is the angle 40. We have the side that's adjacent to it. So that means it would be cos, right? So it would be your 120, which is adjacent to the angle, cos the angle, which is 40. All right, when we do that, we get All right, so when we do that, we get 92 newtons. All right, so this 92 newtons would be the value of RA. All right, so to find the value of RB, let's call it tension 2. It's still, we have the adjacent side to the angle of 50, so it's still cos. So it's 120 cos the new angle now, which is 50. And that would be equal to 77.
77.1. Yeah.
All right, so we get 77 newtons, and that's the value of RP. All right, so everyone got that?
Yes, sir.
All right, so let's look at a worksheet with some other ones with a little bit more complications to it. All right, so here we are at question 1. So in this case, now we have 3 forces acting on an object, right? And the question is to find the x and y component of each 3 forces, right? And find the magnitude and direction of the 4th force, which must be added in order for the resultant force to be 0. All right, so let's go. So we're going to call each separately. So we're going to call this 200 newtons. Let's call it A. All right, we're going to call it 300 B, and 160, I'm going to call it C. So therefore, we can complete these triangles to know. So we have a triangle there. So this is your y component. This is your x component. We can complete this triangle here, this is your y. This is your x. And we also can complete this triangle here, where this is your x and this is your y. All right, so I'm going to do this one on the board. All right, so you're going to tell me what to write for each. So let's start with A. So we're doing the x and the y components for each. So we're starting off with vector A. So for x,
F sine
so we're doing
theta.
for x, the x component first.
Oh.
So for A, the x would be sine or cos.
Cos.
So it's cos theta. Right, and F is 200 cos the angle, which is 30, and we get
173.2.
173.2. Alright, so that's our x component, and then the y component would be sine theta, which is 200 sine 30, which is
100.
100 newtons. Alright, so that's for A. right? And we notice both values would be positive because the x component is going to the right and the y component is going up. So both quantities are positive. All right, let's look at B now. So for x component of B, it's the same adjacent, so it is f cos theta. So in f this time is 300 cos the angle, which is 45. So that is
212.
212 newtons. And then your y component would be f sine theta, which is 300 sine 45, which is
212.
212. Alright, so what would be the sign for your x and your y component for P? So the
Y is positive
X is negative.
and X is negative.
x, right? So x is going to the left, so that's negative. Y is going up, so that's positive. So we can put a negative there to show the direction of x. All right, and finally, we have for vector c, so your x component for vector c is still cos, so it's f cos theta. So the f there is 160 cos the angle, which is 55, and that's equal to
92.
92 newtons. And then your y is f sine theta, which is 160 sine 55, which is equal to
131.
131 newtons. All right, so again, we put in the signs. So x for this one would be
Negative.
negative because it's going to the left, and the y would be
Negative.
Negative.
negative because it's going down. All right, so that's the first part of the question. So we find each x and y component for each vector. All right, so the second part now says find the magnitude of the and direction of the fourth vector that would cause the resultant to be 0. All right, so what do we know when the resultant is 0?
The
Both components
opposite
are
forces are equal.
Great, so the forces are the x and so each x component would be equal to 0, right? And your y components also be equal to 0. So let's look at our x's. So let's find the resultant for your x. All right, so we know for x, for the a is 173.2, right? And for b, it's negative 212, and for c, it's negative 92. So when we add those, we get
477.2.
did you remember you have to put in the
Neg
negatives on these?
Negative
negative
130.8.
30.8.
Negative 130.8 newtons. Right? So if our resultant for these three is 130.8, negative 130.8 newtons, then that means the x component of the fourth vector would be what? Let's solve for vector D. So the x component of D would be
Positive 130.8.
130.8.
exactly the positive 130.8. All right, then we're going to do the same for y. So the resultant of y would be, it's 100 here, plus 212 plus negative 131, and we get
181.
so it's 181. So therefore the d of y would be
Negative 181.
great. So dy would be negative 181 Newton. Alright. So if we have a positive, if we have the positive x and a negative y, then which quadrant would this vector be in? The positive x, negative,
The fourth quadrant.
so it will be in the fourth quadrant. So that means our vector is vector d somewhere here, right? So we have the x component, which is 181.181 for the y, and the x is 130.8, right? So we need to find what d is. So we have both sides of the triangle, we need to find the hypotenuse. So that means we use Pythagoras theorem. So that means d is equal to the square root of 130.8 squared plus 181 squared. And we get
I'm getting 222. I'm not
two,
sure. 223. Yeah, I'm getting.
223.
so we get 223 newtons. So that means the value of d is 223. Alright, so therefore we need to find the direction now, which is to find the angle. Alright, so let's find
Using
this angle here.
tan theta.
So let's use tan theta. Alright. So tan theta is opposite, which is 181 over the
Over
adjacent
adjacent.
130.8. So therefore theta will be
Tan inverse.
tan inverse
181 divided 130.8.
54.8.
54.1.
What's this first? When you divide, what was that? 1 point. So 181 divided by 130.8, you get 1.38.
38.
And then tan inverse of 1.38 is
54.1 degrees.
54.1 degrees. Right? So your fourth vector would be 223 newtons. That's acting 54.1 degrees away from your horizontal there. Or you can write away from 130.8 newtons. All right, so everyone got that?
Yep.
All right, so since question 3 is just like that, I'm going to give you the chance to do question 3, and then you tell me the answers you get. So it says three forces acting on O, shown in figure 3. Find the resultant, their resultant, and clearly indicate the direction of this resultant force with respect to the positive x-axis. All right, so you're finding the total resultant force by those three vectors. All right, so I'm giving some time for you to do that, and you can tell me what's the value of the angle as well as the vector. Any answers as yet? All right, so the time is going to finish. So I'm going to actually disconnect now and restart. And when I restart, I hope we have the answers to this question, all right? So have we received an answer yet? Anyone worked it out and got the answer?
Sir, I'm still working, but you can start without me.
Still? No, I will wait
Sir,
until.
I got 22.14 newtons.
All right. Let's see when someone else. So 22.1. And what's the angle?
Um, one sec. (14.6 degrees).
Okay. In that regards to the x-axis, right?
Um,
Yes.
Okay. All right, so let's work this and see if we get it. All right, so we're going to take the 31 as the 35, sorry. So we're taking this as vector A. All right, we complete this triangle here. So this is your X, this is your Y. And we complete this one here. We're going to call it B. So this is your Y, this is your X. We complete this one here. That's C, where this is your Y, and this is your X. All right, so let's go. So for A, the X component would be, that's opposite, so that's sine. So that's F sine theta. So that is 35 sine 25. And that one you got?
Negative 14. Wait there. Positive 14.79.
8.79.
14.79. That's what I got.
Okay. All right, so we have that. And then for your y component, it would be f cos theta, the 35 cos 25, and we get
31.72.
72 newtons. All right, and we know that y is going up, so that's positive. X is going to the right, so that's also positive. All right, so that's for A. Then for vector B, X would be, it's adjacent to the angle for X, so that is cos, so F cos theta. So F is 20, cos the angle, which is 45, and we get
14.4.14. Sir, 20 costs 45.
yes.
14.14.
Yeah. And then for the Y, it would be F sine theta, so 20 sine 45, and it's the same answer, right?
Yes, sir.
Yeah.
14.14 newton. All right, so B, X is going to the left, so that is a negative. Y is going down, so that's also a negative. All right, and then finally, for C, X there would be adjacent, so it's cos, so that is 24 cos 30, which is
20.78.
20.78, and then the Y would be
12.
F sine theta, 24
12, sir.
12 theta. All
Yeah,
right, so
12.
your X is positive because it's going to the right, Y is negative because it's going down. Alright, so we have those as our vectors. So now it's to find your resultant vector R. So we're finding the X component first, which is to add all our vectors together for X. So the first one is 14.79 plus negative 14.14 plus
Positive
20.7,
20.78.
and they get a little bit more because this and this is not the same. So 21.43,
Mm-hmm.
21.43 newtons, right? And then your Y component would be the 31.72 plus negative 14.14 plus
That's negative.
negative 12, which we get
5.58.
0.58 newtons. Right, so those are the two components of your resultant. So we can find the final value. Right, so both values are positive. So that means it's in your first quadrant here. And so for X is 21.43 and your Y component is 5.58. So that means we need to find this angle here and we find it R there. So r is equal to the square root of 21.43 squared plus 5.58 squared, which we get
Not seeing clearly.
22.14.
22.14 newtons. And then the angle, all right, since we used tan the last time, let's use sine. Sine theta is opposite 5.58 over the hypotenuse r is 22.14. The theta is equal to sine inverse of
Sine inverse of 0.25.
So I normally like using 3 decimal places to make it a little bit more accurate. So 0.252 and we get 14.60 degrees. Right? I think that's what you got.
Yeah.
All right. So in all vector equate or questions, this is the same process that you will do each time. Right? So you resolve your single vectors into its x and your y component. Then you add. Right? So please remember the sign, the negative if they're going down or left. And then you add everything to get your x and y component for your resultant, and then you can find your resultant by using Pythagoras theorem. Then you find the angle by using either sine, cos, or theta. All right, so we're going to move on. All right, so everyone understands vector, so we can move on. That's a yes.
Yes, sir.
All right.
Sir, I'm not seeing the board so clearly, especially over to the side that you did the resultant.
Over this side.
Yes, sir, because I was trying to see exactly what you did right there in the square root.
It's square root of 21.43 squared plus 5.58 squared.
Okay.
All right, so we're going to move to another topic now. Which is, all right, so question, do you guys want me to do some things pertaining to graphs? Or that's okay?
Which graphs, sir? Just overall graphs?
Yes, overall graphs.
Sir, what are the other options?
All right, so if we're not doing graph, then we'll move on to units, quantities and units, and then motion.
Oh, sir, we can do graphs. We can just do everything.
Okay. All right, so we're not going to
That's my
do,
opinion, though. That's just my
so we're not going to do plotting the graphs, but there are just some little things that you need to know pertaining to graphs. That's what we're going to do. All right, so we're just going to look at how do we get exponential equation to actually look like a straight line graph in order for you to get a straight line from that. All right, so that's what we're going to look at. All right, so if so in physics, we don't have all equations that look like the y equals mx plus c, right? Because we know that to draw a straight line, your equation for that straight line has to look like y equals mx plus c, right? Now, if we look at that slide there, we see an equation that says v is equal to k r to the n power, right? So in this case, we would ask you to plot v, so a quantity of v versus r. So if we ask you to plot a quantity of v versus r, we notice that r has a power here, and r represents your x component. So if we ask you to find r, right, we notice there is no power of x in your y equals mx plus c. So it's impossible to, by using this equation alone, to actually plot this graph and you get a straight line, right? The only way you will get a straight line is if we ask you to plot r to the n power. So r to the n would be equal to the x, right? But if it's just r, then you will not get a straight line. So to get this equation to look like this, then that means we have to know these characteristics of log, right? So we log equations that have power in order to actually get a straight line equation for that specific equation. So if we look at this, if we log both sides, right, then we have log v is equal to log, and we log in this, right? So it's log k times r. Now if we notice, rule 1 says that if we log k times r is the same as
Log
log
K.
of k plus log of r to the n, right? But if we look at log 3, rule 3 again, it says that if you log something that has a power, it's the same as taking down the power to be in front of the log. So therefore, this equation now be log v is equal to log k plus n log r. All right? So that's using two of the rules to actually change this equation to a straight line equation. Now, if we look at this now, we see that instead of plotting v on your y-axis, we're going to plot log of v on your y-axis, right? Instead of plotting r, we're going to plot log or r on your x-axis. So therefore, what would be your gradient equal to for this equation?
N.
N.
So n here would represent your gradient, and this log k would represent
C.
Intercept.
your y-intercept c. So let's look at certain things in this, right? Now, as a teacher, the certain things I look for to see if a graph is actually right, especially the best fit line. Now, if you're supposed to plot this graph, right, and you have your axis and your scale, and you start at 0 with your scale here. If by any chance you plot and your best fit line goes through 0, then that is wrong. Right? So if your best fit line goes through 0, it's wrong. And let's show you why. Because based on your equation, you're supposed to get that log k should be your y-intercept. This y-intercept is 0, right? So in this case, log k cannot be equal to 0. So that's one thing that you'd pay attention to when you're doing graphs. If you do have a y-intercept, then that means there's no way your best fit line is going to actually pass it through the origin. Right? So that's one thing to look for when you're plotting graphs. Right? Now, so this equation is easier. Right? Let's find one that is a little bit more challenging. All right, let's do the last one on this, which is this one. All right, so that equation there. All right, and we're also going to look at filling out tables because there are certain things that you need to note when you're filling out a table. All right, so the equation is G minus A is equal to B over M times V to the N. All right, so G minus A is noted as just being one variable there. So we're not going to split the G minus A. All right, so you're going to tell me how you're going to move to making this be a straight line graph, because obviously we have a power there that we need to actually remove. All right, so the first thing we do is
log both sides.
so we log both sides. So we're going to log the G minus A equals the log of B over M times Vn. All right, so let's simplify over there. So simplifying that side, we get
Log B
so doing the
minus
Log
multiplying
B
first.
minus log M plus N log
So log E minus log M plus
plus N log V.
so N log V. Right?
Remember the log G minus A.
Then this part here. So therefore we note that the log G minus A would be your Y. So that's going on your Y. Then log V will be going on your X. So therefore your gradient is
N.
N.
so your gradient is N. And therefore this here represents your
Y-intercept.
Y-intercept. Right, so it's key to note. So that's the reason why I bracketed here, because some persons would think that it's one of these things that would be the y-intercept, either this or this, right? But remember, it only can be y equals mx plus c. So you have the y, you have the m, and you have the x. So therefore, whatever remains would be your y-intercept. All right, so that's how you would use any equation to actually break it down to get a straight line graph mimicking the y equals mx plus c, right? And please note that not all the time your m will just be one thing beside it, right? Your m can actually be more than just one symbol beside. Let's see. All right, let's use the pendulum equation. All right, so pendulum equation, if we log this, we get this. All right, so we get that. So obviously, we would have to divide by 2 to get the log t. So log t would be, so this here is your y, right? G is a constant, so it cannot be your x. So log L is your x. So 2 pi is your gradient, and also this would be your y-intercept. So we notice that it's not just one thing here, that's your gradient. Your gradient is 2 pi, right? And that's how, even at the CXC level, that's how us as teachers know if your gradient is actually the right value, right? Because your gradient should be, especially for pendulum, your gradient should be a certain value in order for you to actually get an accurate value or close to an accurate value of G, right? So that's key to note about plotting your graph. So before you plot any graph at cape level, once you have the equation, the first thing is to do is to actually get your equation to look like y equals mx plus c. All right. Now let's look at the table. So things to do when you're actually filling out a table. So unless your instruction tells you to give you to a specific decimal place or significant figures, then that means you should use the principle. Now, the principle is each quantity of the each column of the same quantity should always should always have the same significant figures, right? So let's look. So column A is acceleration, column B is velocity. The third column is G minus A, which is basically a difference in acceleration. So your third column, when you're filling out these values should have the same significant figures as these values, right? Now, if you calculate these values and you notice that at a point like 2 values are the same, right? Then your instruction would be that you increase the significant figure to 1 more, right? So let's say if when you're filling out, you got 0.02 for one, and then the next one is 0.02, right? In cases like those, you would have actually gotten instruction to, instead of using 3 significant figures, you should use 4. So those are the only cases where you don't abide by the rule, when 2 or more of the values are going to be the same, right? But it will be instructed if that's the case, so you can actually know before you start. So in this case, you'll ensure that these would be actually 3 significant figure values because they are acceleration, just like acceleration there, right? And the same thing applies for this. Log of G minus A, it's G minus A, so these also will be 3 significant figures. Log of B, B here is 2 significant figures, so therefore you use 2 significant figures for those, right? So that's the principle of filling out your tables, right? But Cape normally tells you the amount of significant figures to use, but just in case it's not given, that's how you would actually know how much you need to actually use. All right, so that's basically what all we're going to look for in terms of graphs and tables. All right, so we're going to now look at units to show dimensional analysis and such. All right, so let's look at units. All right, so before we look at units, these terms are terms that you should be aware of: accuracy and precision. So accuracy is the degree to which a measurement approaches the true value. And you know the true value would be the actual value of the reading for the specific quantity that you're measuring, right? So accuracy means how close you're actually to your true value, while precision actually refers to the closeness of two or more measurements to each other. So in precision, it's how close when you redo this experiment or measurement, or do you have two values or three values that are close to each other. It doesn't necessarily mean that it will be close to your accurate value, right? So let's say you measure a table, right? The actual length of the table, let's say, is 25 centimeters, right? So you measure something, the actual or the true value is 25, but each time you measure it at 23 or 24, right? So it's not accurate, but because the values that you get are close to each other, they are precise. So accuracy, so precision does not necessarily means accuracy, right? So precision could mean that you're doing something wrong, but you're getting answers close together, but you're doing something wrong to not get your true value. All right, so that's something that you should be aware of, especially in physics where we do a lot of measurements. All right, so if we look at the reading of the diameter from a vernier caliper, so the meter rule gives 1.2 plus or minus 0.1 centimeters. So thing to note is that your meter ruler can only give you one decimal place of value, right? Because it's measured in centimeters, you only have a one decimal place of value, right? Vernier caliper now, you can actually get up to two decimal places in terms of your centimeter value. And for micrometer screw gauge, it gets up to three decimal places in reading, right? So the degree of precision to which the measurement is made increases as we move from the meter rule to your vernier caliper and finally to your micrometer screw gauge. So precision in this case means that how deep can you get into the reading, right? So it's just like your phone. So some phones, you zoom in on your figure to get a more detailed look at it. So that's what is being shown here. So your meter rule would be just a normal picture that you take. The vernier one is like if you zoom in like times one zoom in, right? And your micrometer screw gauge would be like your time two zoom in. So each time you zoom in, you're actually seeing something that you could not see before you zoom in to that specific point. So that is precision in terms of your reading instruments. So reading instruments precision means how much decimal places it actually can give you. So it makes it more accurate, right? So when a measurement is repeated many times with a precise instrument, the readings are all close together, right? So if you use a precise instrument, in such case, if you use a micrometer screw gauge, right? So each time you actually carry out the experiment, you're actually getting more a precise reading, right? So the normal things that we normally use for precision and accuracy is a dartboard, right? So if we look at these three diagrams, the first one on the left shows us that the true value is that red spot. So that's their aim. So that's the true value, right? So all three darts are actually in the red spot. So we have good accuracy because they're in the true value. And they're precise because all of them are actually in the same reading value, right? The middle one there, now all of them are outside the true value, so they are poor accuracy, right? But they're good precision because they're all close together. And then final one on the right shows us that they are still not in the red spot, the true value, so they're poor accuracy. But this case, they're all over at different locations. So that means they have poor precision as well, right? Because they're not close together, their precision is not good. All right, so we look now at the uncertainty measurements. So the total range of values within the measurement is likely to lie is known as your uncertainty. So it's basically a doubt of your measurement, which is the smallest division on a scale. So let's look what exactly that means. All right, so if you use a ruler, right, you notice that each small readings on your centimeter ruler is 0.1, right? So in what uncertainty is, it's saying that if you use your ruler to measure an object and you get 2.1 centimeters, that 0.1, so that reading can actually be less than that or that value or more than that, but how much more or less it can be. So the uncertainty tells you how much more or less the value actually can be, because with measuring instruments, when they are being manufactured, they can actually get problems or issues will actually arise that your instrument is not made properly in terms of the scales, right? So if you actually use more than one rulers, right, and you measure an object, especially if it's to a point place, it's going to actually, some of those rulers will give you a different reading, right? And those rulers can be very new. And that's because, could be because the materials that they're made from, right? Or the manufacturing errors that happened when it was being produced. So that's what uncertainty tells us, right? So for example, a measurement of 46.0 plus or minus 0.5 centimeters. So the 0.5 centimeters is your uncertainty. So that's the smallest line on that measuring instrument. So it can be 0.1 centimeters. So in this case, the actual value of the reading can be either 46, so 46 there, or it can be 46 minus 0.5, which is 45.5, or it can be 46 plus 0.5, which is 46.5 centimeters, right? So let's look at if, because that's just if it's one measuring instrument. So what if we have an equation, right? And we're combining different instruments uncertainties together to get the uncertainty of an unknown quantity. So in these cases, we have to know these principles. So if the equation is a plus equation, so we have plus, so we have, in this case, is x equals y plus z. So the uncertainty in x, which is delta x, would be the uncertainty in y plus the uncertainty in z. Or if it's a negative in the equation, it's the same, uncertainty in x equal uncertainty in y plus uncertainty in z. So it doesn't matter if it's a plus or a negative, in your equation, your uncertainties will be added together, right? So that's what that is saying. So example, so if we have a current I1 and I2 going into a junction in a circuit, the current I going out of the junction is equal to, you're adding the two currents together to give you I, right? So we have I1 and I2. So I1 is 2.0 plus or minus 0.1 amps, I2 is 1.5 plus or minus 0.2 amps. What is the value of I and its uncertainty? So to find I, we know that we just add both I1 and I2. So it's 2.0 plus 1.5, which we get 3.5. So that's the value of I. But the uncertainty would be because this value is, because in the equation, right? So as I was saying that, because your equation here has a plus sign, then that means we use this principle here that says the uncertainty in x equals uncertainty in y plus uncertainty in z. So we have the uncertainty in I will be equal to the uncertainty in I1 plus uncertainty in I2. So the uncertainty in I1 is 0.1 plus the uncertainty in I2, which is 0.2. So we get a total uncertainty of 0.3 amps. So therefore, your final answer will be that I is equal to 3.5 plus or minus 0.3 amps, right? So let's look at if it's in case of multiplication or division will be the same, right? So in multiplication, we use what is known as a fractional uncertainty, which is the uncertainty of the value divided by the value, the actual value of that quantity. So in this case, we have x equals AYZ, where A is a constant. And in this case, what a constant is basically it's something that is not measured by a measuring instrument. So just like the value of gravitational acceleration, we don't use a instrument to measure that value. It's done based on calculations, right? So there is no instrument to measure it. So there, it's known as a constant in this case. So in that case, then we can eliminate A from this because it doesn't have an uncertainty. So we have the uncertainty in x divided by the value of x equals the uncertainty in y divided by y plus the uncertainty in z divided by z. And in a case where there is powers to these values, then it resembles looking like a log. So the powers will actually be brought down to multiply by the fractional uncertainty. All right, so we're going to look at these now in a different light. So let's look at this question. All right, so in this question, it tells us that the volume of a measuring, the volume of a sphere is 4 pi squared L of a cylinder star, right? And it gives us that R is 3.30 plus or minus 0.05 centimeters. It gives us that L is 25.4 plus or minus 0.4 centimeters, right? And we need to find what is V and delta V. All right, so in this case, we notice that it's multiplication. So we have to use our fractional uncertainty, right? And we also know that pi here is a constant, which is not measured by a measuring instrument. So we can eliminate it. So we have V is equal to R squared L, right? So in this case, first we find the value of V. So V is equal to pi squared L. So we need to find what that value is. So it's 3.14 multiplied by R, and R is 3.30 squared multiplied by L, which is 25.4. So we find the value of R first, of V, sorry, first. And in that case, V would be so you get the volume of this to be 868.54 centimeters cubed. Right? So now we can find
868.9.
0.54, yes. All right, so we can find the uncertainty in the volume now. So it's uncertainty in volume over the value of the
So
volume equals the 2. We take down
sir,
the
what's
2,
the value you got?
868.54.
Exact pi value from the calculator?
What's that?
Did you use the exact pi value on the calculator or?
No, I just used 3.14.
Okay, that's why. Okay.
Oh.
Continuously.
All right, so we take down the 2 from the R, so it becomes 2 here, and we find the uncertainty in R over R plus L, which is the uncertainty in L over L. Right, so the aim here is to find the uncertainty in V. Right, so in this case, uncertainty in V would be the value of V, which is 868.54 equals 2 times the uncertainty in R, which is 0.05 over the value of R, which is 3.30, plus the uncertainty in L, which is 0.4 over the value of L, which is 25.4. All right, so we're going to do everything on the right side one time. So that's 2. All right, so everything on the right side would be equal to 0.0 0.046, we can just have 0.05. Right, so therefore the uncertainty in V would be to multiply these two and we get 43.43 centimeters. Right? So your value of V is that, and your uncertainty is 43.43. Right? So we notice here that even though your uncertainties that make up volume, R and L, they are very small uncertainties. Your value for your uncertainty of your volume is actually relatively a bigger number than these, right? So that shows us that if we're finding the volume of an object and we're using this method, meaning to find the radius and to find the length, we're going to get more uncertainty in your value rather than if you will actually use a measuring instrument to find the volume of that specific object, right? So let's say we had the water in a measuring cylinder and you find the volume of that water, it would have less uncertainty in that volume than if you use measuring instrument to find the diameter of the radius of your measuring cylinder and then find the length and do this. If you do this, you get a higher uncertainty in your value than if you just use a measuring instrument to find the value of your volume, right? So that's something that you look keenly at. It doesn't matter if it's multiplication or addition. Your uncertainties will always add up to be a bigger number than your individual uncertainties. So that's the reason why for quantities, we actually develop measuring instruments to measure each quantity to actually reduce this value. So if you're not using a measuring instrument and you're using by calculations method, it's going to actually add up to give you a bigger uncertainty value.
Excuse me, sir.
Uh-huh.
What's the unit for the uncertainty of V?
Oh, volume cube, sorry. Centimeters cube.
Okay.
All right, so that's basically what you do for uncertainties. All right, so we're going to look at the units part of this. Right, so we're looking at our base units, which are those 7 units there. From CSEC level, you learned the first 5. So the only addition here is the amount of substance and the luminous intensity. The amount of substance is mole, which is a unit of mole, and luminous intensity is candela, right? So the unit of luminous intensity is candela. So those are things that you need to know, as well as your prefixes. So these are the prefixes that they normally give you, so you need to know what each value of those prefixes are, because they're not going to actually tell you. Right, so let's look at homogeneous equations. So homogeneous equations mean that the total units on your left side of your equation has to match up with the total units on your right side of the equation, sorry. So that's what homogeneous equations mean. So if we look at this one that says work is equal to gain in kinetic energy plus gain in gravitational potential energy. So let's find the unit of work done, which is work we know is force times distance, and force there is measured in newtons, or it's kilogram meters per second squared, because force is mass times acceleration. So it's kilogram meters per second squared times the distance, which is measured in meters. So we get kilogram meters squared per second squared. So we have that part here for the work done. So that's our unit, right? And then in an equation that has plus or minus, right, we don't have to find for both, because if you're adding kinetic energy and potential energy, they both have the same units. So we could just focus on one of those, right? But in this case, we did both. So for kinetic energy, we know it's half mv squared. So half is not a unit, it's a constant, so you ignore that. So its mass is measured in kilograms, right? And speed is meters per second, but it's squared. So we squared that meters per second, right? So we get kilogram meters squared per second squared, right? So we notice that these two are the same, right? And just to ensure that the potential energy is the same as well, we find it. So potential energy is mass times G times H. So mass is measured in kilograms, G is measured in meters per second squared, and H is measured in meters. So we get kilogram meters per times meters is meters squared per second squared. So all three quantities have the same unit. So in this case, we say that the equation is homogeneous. All right, everyone got that?
Yes, sir.
Yes, sir.
Alright, so in terms of homogeneous equations, sometimes the question is specific. Instead of doing it for its units, kg, m, or seconds, it normally asks you, or sometimes asks you for dimensional analysis, which is the same process. It just means that if it's specific to dimensional analysis, we have to use these units instead of the kg and the m and the s, right? So for length, anything that has distance, length, right? We use a capital L, meters squared. So we're only using these, right? If it's time, then it's a capital T. And if it's mass, it's a capital M. So those are the three things that you need to know. For dimensional analysis, if an equation has length or distance, we replace it with a capital L. If it has mass in it, we replace it with a capital M. And if it has time, we replace it with a capital T. And then you work. So let's look at what's the dimensional form of the equation x equals half at squared. So we know x is a distance, right? So x will replace that distance with L. So on the left side, we just have L. And then on the right side, remember half has no unit, so we're going to ignore that. And A, remember A acceleration is velocity over time, which is actually distance over time squared. So in that case, distance is L, time, so it's t squared, capital T squared, multiplied by t squared there, so it's t squared again, so both t squares get cancelled, so we leave back with L equals L, and we show that it is homogeneous. All right, so let's look at the first question here. So to show that the expression v equals at, where v is speed, a is acceleration, t is time, is dimensionally correct. All right, so let's go. So you're going to tell me what to write.
L over T.
So we know for v, so let's write the equation. So for v, we're going to have distance over time, which is distance is L, and time is capital T, right? And that's equal to a, which
L over T
T
squared.
squared.
L over T squared. So that's for A, and then it's multiplied by T, which is a capital T. Right, so we notice we can cancel this T and one of this T. So we are left back with L over T. Right, so we see that this equation is dimensionally correct. Because both left and right are equal. Right? Let's look at the next part. Suppose we are told that the acceleration A of a particle moving with a uniform speed v in a circle of radius r is proportional to some power of r, say r to the n power, and some power of v, say v to the m. Determine the values of n and m and write the simplest form of the equation for acceleration. Alright, so this now will need some little thinking. Alright, so it says that A acceleration of a particle is proportional, so we put the proportional sign, so it's proportional to R and V, but it's R to the N and V to the M power, right? So in this case, we have to use dimensional analysis to see what could be the possible values of N and M. So we know that acceleration is L over T squared,
T squared.
right? And that's proportional to R is a length, so it's L to the M. V there is speed, so that is L over T. and this is to the m powers, right? So we notice now that these two are the same, so we can have, if we multiply two same bases, then what do we do with the powers?
Add the powers.
We add, so it's Lm plus n over t to the m, right? But we know this, right? So the only t that's on the right side should be the amount of t on the left side, correct? So we have t squared here, so that means this m has to be
Squared.
squared. So that means the m is equal to 2, because t squared has to be equal to t to the m. So therefore 2 is equal to m, right? So we know the value of m, so therefore we can use it now to find what n is. So at the top here, we know this is 1, so it's basically 1 is equal to n plus m, right? And we know m is 2, so it's 1 equal n plus 2. We take the 2 over, so therefore n would be equal to 1 minus 2, which is minus 1, right? So therefore we can write the equation, which would be that A is equal to R, n is negative 1, so therefore, and B is 2, the m is 2, so that's 2 over R, right? Because remember, n is negative 1, so you put negative 1 here, that means just 1 over R. So we simplify it and we get that equation there. Right? Everyone got that? Yes, guys, is that clear?
Yeah.
Yes, sir.
All right, great. All right, so let's look at some questions pertaining to this. All right, so question 1. So the force F of a mass m1 due to another mass m2 is given by F equals g m1 m2 over 4 pi r squared, where r is the distance separated between m and m1 and m2. Find the unit of g. All right, so because we're looking at the unit of g, then that means this equation is homogeneous. All right, so if it's homogeneous, then that means your left unit equal to your right unit. So let's look at the left, so the left unit first. And on the left unit, we only have force. And we know force is equal to MA, right? So M is measured in kilograms, A is measured in meters per second squared. So that means your right side equation has the total equation equals to that, right? So your left side equation is kilogram meters per second squared. All right, let's write this like this to make it easy if we're going to cancel something. Is equal to, so your G is unknown, so we're going to write back the G there, multiplied by M1, the unit of M1 is kilogram, times M2, kilograms again, over the 4 pi is a constant, so we ignore that, over r squared. R is distance, so it's meter squared. Right? So we can simplify So you get kilogram meters over second squared is equal to G. Kilograms times kilograms is kilogram squared over meter squared. Alright, so what do we do from here? Alright, so we make G the subject. So that means we multiply this side by m squared over kg squared. And we do the same here. So we can cancel these to leave back with G, right? And 1 kg here can cancel 1 here. And this m and m goes together. So therefore, the unit here would be m squared times m, which is m cubed. And that's the only thing at the top. And at the bottom is kg and s squared. So that unit is meter cubed per kilogram per second squared. So that's what we would get. All right, is that clear?
Yes, sir.
Yes.
All right, so using that same principle, we're going to do question 3. All right, but this time we're finding what CD unit is. And it says that we need to show that CD is dimensionless. And dimensionless would mean that it has no unit. So that means everything on your right side should cancel out, so we get no units there. Right? So we have CD is equal to force over, we're going to ignore the half there because it's not going to affect the answer. Rho v squared A. Alright, so let's go. So force we know is mass times acceleration, so meters per second squared, right? Divided by rho, which is density, which is mass over volume per kilogram per cubic meter, right? And V there represents the, where is V? V speed. Speed is meters per second times A, which here is your area, which is meters squared. Right, so let's simplify first. So that's kilograms.
Third V squared.
Oh, yeah, so this is squared, so it's meters squared per second squared there. All right, so that's divided by, so kg, meters squared times meters squared is meters to the fourth over meter cube second squared. All right, we can cancel this cube and this to leave 1. Now we can flip to get rid of the division sign. So it's kg meters over s squared times, so we flip in, so s squared goes at the top over kg m. Right? So we notice now that the m cancel, kg cancel, the s squared cancels. So we leave back with no units. So that shows us that CD is dimensionless. So it has no units. All right, that's clear.
Sir.
All right, so with that said, you're going to try the last question for the last 5 minutes that we have remaining. All right, so go ahead and so you're finding the value of x, y, and z, just like how we did it for the previous question to this. All right, so go ahead and try that one and tell me what you got for your values. And also please note that k there is a constant, so that means it has no unit. Any answers so far?
Z negative 1/2.
No answers as yet?
Sir, I got and don't think they're correct.
Alright,
I'm
what did
waiting
you?
on it.
I got someone else's answer. Someone got x to be 0, y to be a half, and z to be negative a half. That's what you got?
No, sir.
All right, we have 2 minutes, so let me start it off and see if we can finish in that time. All right, so using dimensional analysis, T would be same T, mass would be M to the X, length would be L to the Y, and G here is acceleration, which is length over T squared, but this is 2Z. That's what most persons got.
Yes, sir.
Yes.
All right, so we can simplify these L's. So it's adding, so it's L Y plus Z over T to Z. So we notice that there's no M on this side, so that M there shows that X is equal to 0, right? Because there's no M on the left side. Right? Now we know that we have the T's here. So this T is a 1. And that T there is that. So how do we equate this?
2Z
So,
equals 1.
so this one is
I'm
equal,
making
because it's being divided here, it's a negative 2Z. Right? Because the T is divided here. So this is 1 equals 1 over this, which is negative 2Z. Alright, so we get z to be negative a half because this is 1 over t. So this is negative 2z equals the 1. Right? And then for the L, there is no L here. So this is 0, right? And it's equal to the L here, which is y plus z. So we know z here is a negative a half, so it's 0, y minus a half. So we take this over, so y becomes positive a half. Right? So we have x0, z negative a half, and y is positive a half. All right, so I think that's what the person I got from got. That's what everybody got. All right, so that's how you would use dimensional analysis to actually give you the unknown indices from each. Right, so obviously that x is 0 because there is no m on the left, so therefore this x is 0. The t here is 1 on this side. This one, because it's being divided by, it's negative 2z, right? So we divide by 2, negative 2 on each side, so we get z to be at negative a half. And then y, there is no l on this side, so it's 0 on the left side. And on the y, it's y plus z, and we know z is a negative a half. And then we carry it over, so y is positive a half. All right, so that's clear.
Yes, sir.
Yes, sir.
All right, so that's it, guys. Thanks for coming, and hope you understand and learn something today. All right, so see you guys next week.
Okay,
Thank
sir.
you.
You're
Thank
welcome.
you.
Thank you.
You're welcome.